So far, we have seen enumerative types. These are types which take values from a finite set of options. So for example, the suit type was enumerative in that you could only pick between the diamonds, clubs, hearts and spades options. You couldn't, for example, generate anything outside of those options. However, in Haskell, we can also define recursive types, and we can define more complex recursive types. However, to start with, I'd like us to think about the natural numbers. Now, in this case, we take the natural numbers to be either 0 or a successor of another natural number. So, for example, the number 1 under this definition would be the successor of 0, and the number 2 would be the successor of 0. So essentially, you use successor to count the number of positions you are away from 0. So let's see how we define a recursive type in Haskell. And the definition is actually quite straightforward. So we'll call it nat, and it's going to be equal to either 0 or a successor of a natural number. So you can see here, this is where we make the recursive call to the type definition itself. If I could type properly anyway, that might even work. So we either get the value of 0 or we get a successor of another natural number. So of course, when you make this recursive call, you could either go to here and you could just get successor of 0, or you could go back to here and you get the successor of another natural number. And I'm going to stick deriving show, just so that we can print this out without worrying too much. And I'll reload this into Haskell. And one thing that's quite interesting about this is because our successor is actually a recursive call, that means that it becomes a function under Haskell's definition. So while it's part of the type signature, we can say colon t. This is a function from natural numbers to natural numbers, because if you look at this definition, successor needs to take a value in order to produce a result. So successor needs to be given a function argument in order to return something. But that's nothing too much to worry about, that's just an aside. So let's see how we work with this. Let's do some basic stuff. So one thing we can do is we can convert this to integer. So because this is a definition of natural numbers, we can convert over to a positive integer quite easily. So let's say we do to int, and we're going to say nat to int, and we're going to say this is going to be something. So let's think about how we would define this. We want to count up the number of successors. So for example, successor of 0 is 1. So every time we see a successor, we want to add 1 to the total. But of course, that means when we get 0, we just return 0. And then when we get successor, put that in brackets, of say x, we just do 1 plus to int of x. And this is very similar to a lot of the length functions we've written. We just do a recursive call, counting as we go, using the base case to eventually generate the value we're looking for. So that's relatively straightforward. So let's save this, and if we come back into here, we can do to int, and a natural number under this definition should look something like this. So let's say give it this the natural number 3. And of course it does count this appropriately. It just counts the number of successors we have and then returning 0 when we get to 0. So that's pretty simple. Something that's a little bit more complex is how do we define addition for this type? Because this is a bit more of a complex type. When your natural numbers look like this, it's not necessarily clear how you would add two of them together. So let's think about this. First, I'm just going to specify the type definition, or the type signature, whatever we're calling it these days. And I'm going to say we take an x, and I'm not going to specify the second number because I'm going to say this should be the base case of 0. This is where we normally start with our recursion. Of course, we're going to be using recursion here because that's what we do in Haskell. But what do I do when I add 0 to a number? Well, in that case, I just return the other number. So I just return x, not xargs. I seem to love importing this. But this is our base case. When one of the numbers is reduced to 0, the number on the right hand side is reduced to 0, we can just return the left hand element because we know that that's not going to change anything. So let's say we have an x, and then on the other hand we have the successor of y. Now what do we do? It seems a little bit more complicated, but what we can think of this as essentially stripping one off the right hand number at a time. So we can strip 1 off, add this to the total, and then work that way. So for example, that's like saying 6 plus 5 is really equal to 1 plus brackets 6 plus 4. So you strip a 1 off the 5, add it to the overall thing, and then you keep going, and eventually we'll get to the 0 case where everything can be added back together. So the way that we do this under this definition is we say that the successor gets stripped to the outside, and it's going to be the successor of add x, y. So we strip this one away. That ensures that we're moving towards the base case, and we wrap around the outside so that we keep a hold of it, and but then it means that we can still keep moving towards that base case. So this one is relatively straightforward. Let's save it and load it into Haskell. And let's do add, let's do a small number. So we'll do, so we need to put a bracket around that. Do successor of 0. So that's 2. Let's add to that 2 again. So here you can see that I get 4 out because we're just stripping them out, keeping a hold of the successors, and then putting them all back together at the end. So this one is relatively simple, and in fact arithmetic under this definition of natural numbers follows a certain pattern. So let's do multiplication. There we go, and again we're going to want to start with the same base case. So we have an x and we have a 0. So what happens when I multiply a number by 0? Well, I should get 0 out. So this should return 0. This is slightly different from addition in this sense, that we get a 0 when we multiply by 0, but that is still going to be what our base case is. So let's think about what should happen when we have an x and we have a successor of a y. So this is a little bit trickier because it's not quite as straightforward as adding things together. So what we need to do is to figure out what multiplication really is. So if I say 5 times 3, that means either 5 lots of 3 or 3 lots of 5. So what we do is, when we multiply, is really repeated addition. So that's one way that we can think about this, is we can think we should be adding a value on as we go. So let's say we're going to have an add, and what we're going to keep in here is multiply x and y, but we're going to add this to a value of x. So let's just get one lot of x, and we're multiplying again, but we're going to add that all together. So we're going to keep stripping away a successor element, multiplying by x as we go, and that'll allow us to do the sort of adding the lots of the numbers together. So let's save this, and if we reload, and let's say we do mult, if we do this with 2 and 2, we should get 4 again. In this case it should be the same as the addition. So let's say we want to make this a little bit bigger, so let's say successor, and add 2 brackets onto the end here, so this should give us back something along the lines of 8. And of course that's quite a lot to read, but that is 8. In fact, what we can do is we can 2int this whole thing, and we do indeed get 8 out. Now you can carry this forward, you can do exponentiation, that's similar to this process, but instead of doing this trick with the adding, you do it with the multiplying. But this is just to give you an idea of how you would work with some other types, which are maybe a little less straightforward to work with. We will see more complex types as we go through this class, but for now this is everything I wanted to cover today. If you have any questions about any of this, please do let me know. Thanks.